Hello and good day. So for this video, let's talk about inverse functions, no? And there are many definition of inverse function depending on what we're talking about. But yeah, on the PDF that I send you, there is a sort of a a quick or a short 2-3 pages of um definitions and explanation and proof on what are the inverse functions, no? But yeah, I think those are important also, but let's go ahead to yeah, exponential and logarithmic functions. So I think these functions are already familiar to you. In fact, this has been already taught in the algebra, no? And just a quick recap. Okay, so let's start with exponential functions, no? So I'll just skip the writing part and paste this one. So yeah, we have here law of exponents, no? And there are four scenarios that we could see in the figure. So yeah, for the laws of exponents, so if x and y are real numbers, no? And also a and the b, as you can show all below of the statement, should be greater than zero, or else still you lead to math error, no? And yeah, for the first one, that would be the addition of exponents, wherein if you have the same base or same b, and yeah, you have the exponent, no? Let's say different values of exponent, then you could combine the exponent, and no, you can add the exponent with the same base. Second statement would be if the scenario would be the division, then it will be the difference. I think there's no, I think this is already understandable. This is just a quick recap. Then if their exponent are interacted with a parenthesis, let's say the quantity of bx, no, quantity raised to the exponent of y, then you will multiply the exponent of x and y. And for the last would be if there are two terms or two variables, parenthesis with an exponent, then you will raise of each variables to the whatever the exponent, no, let's say the quantity of ab raised to the exponent x, then it will be equals to ax or a to the power of x uh times b to the power of x, just what I underlined this one. Okay, and yeah, for the graph of this, let's just say I'll just copy again here, no. So this is normally the graph of an exponential function. We have three lines as we can show in the figure, with the green, the red, and the blue. So y is equal to 0.x, and y is equal to 0.5x, and y is equal to 0.2x. And normally, for each kind of simple exponential function, like a one value raised to exponent of x, all of those lines meet at 1, diba? If you say this is just a normal exponential function, I'm not saying that all types of exponential, because if you'll add something here, no, it will change. It will not meet to 1, no. So, but however, for normal exponential function, it will meet at 1, uh, 0, right? I don't know, bali pala. 0 and 1, actually. So, yeah. So, any type of base or any value of base raised to exponent x, all of the lines will meet at 1, no? At y is equals to 1. So, yeah. So what are the other things that we could do for a recap for exponential functions? Well, I think that's it now. But, yeah. So that is for the exponential function. And we go ahead to logarithmic functions. So logarithmic functions, as we know, it is related to exponential functions, no? Um, as what I've said, this is all about inverse functions, and the inverse of the exponential functions are what we call the logarithmic functions. No, so we could say this here. So let's just say that the log base x with the yeah, how could we pronounce it? Yeah. Yeah, the log x base b is equals to y, which is equivalent to, yeah, b raised to the power of y is equals to x. So it is just how we translate the exponential function to logarithmic functions, no? And it's very important to know this is because whenever we want to find the value of a certain variable that is unknown, we cannot solve it through algebra if the certain equation is in an exponential form. Usually we translate that equation to a logarithmic equation or logarithmic function so that we could solve the value of x in the exponent. So that's how we usually solve for algebra, no? That's why it is very important to know stuffs about this, right? So yeah. And we have here relationship, just uh, con- a follow-up statement. Uh, yeah, the log of b raised to the power x with base b is just equals to x. So if the the base and the value of the logarithmic, which is just the same, then it is just equivalent to the x, no? Yeah. And in reverse, if the b raised to the power of log b, log x base b, so it is just equivalent to the x. So I think this has already been taught also. Actually, there is somewhat familiar, same scenarios to this, pero they lang to logarithmic. But actually, we are talking about uh, Euler functions, right? Exponential functions. Atong Euler number. And the inverse functions of the exponential function are the natural logarithmic. So yeah, and we proceed. Follow-up statement for this one also, we have the rules or the logarithmic law. No? If we have the exponential law, we also have the logarithmic law. Okay, for the product of logarithmic law, it is just equal to the sum of each logarithmic, no? Should be with the same base. So if you have already the product, you could separate that one just like this, no? As what you can see in this figure. Again, this is just a sort of review. And by division, yeah, it is the difference between the separate logarithmics of different variables with the same base, no? Or the same different values with the same base. And for this one, if your logarithmic of x has a exponent, let's say r, no? You could translate that as your numerical coefficient of your logarithmic function. Could transfer it to the left hand side of the logarithmic functions, no? This way you could simplify any kinds of logarithmic functions. So let's proceed. Yeah. again, there are types of logarithmic functions, no? And the special this special function is what we call the natural logarithmic, right? So if you want to know about natural logarithmic, the base of the natural logarithmic is what we call the Euler number, diba? We say that, ano ba to? Yeah, uh the log x with base e, or the Euler number, is just it is just another form of the ln x. And just a quick fact, mas una na discover ang ln x, or the natural logarithmic x, than those of the logarithmic functions with different values of bases. Usually they describe the logarithmic functions in a constant base, which is the Euler number. Yeah, from Euler himself, no? And yeah, for the translation of the Euler number, this is equal to, yeah, the ln of x is equals to y, is just equivalent to the exponential function, or exponential of y, is equals to x, no? So even though we don't write the base e here, we understood it because it is in ln, not in log. So yeah, just the same scenario with logarithmic functions, mo ni siya, no? And same scenario with the logarithmic law, same applications, no, katong division, multiplication, katong yang rule. So yeah, let's go ahead to its graph, no? So these are the graph of the exponential, and its difference, its relation to the logarithmic function, no? As you can see, if you take the logarithmic function of 2x, it will be equivalent to log x base 2. And the graph of it, it's just the mirror of the original exponential function, but its reference line is the diagonal line of the Cartesian plane, which is the green line. So, mirror siya, ana. No? So, sort of inverse function siya sa atong exponential function. Okay? And yeah, same scenario with our exponential function with Euler number, or with natural logarithm. So, yeah, this one. So, this is the graph of y is equals to, I cannot, it's a need to transfer this. Yeah. So same scenario with the logarithmic functions. So for natural logarithmic, it is just a mirror of the exponential functions with the base e, or the Euler number. The reference mirror line is the green line, of course, no? So normally, the inverse function of exponential functions are the logarithmic or the natural logarithmic. Now, since this is all about differentiation, this course, now we need to know what is... yeah, before we go ahead to its differentiation formulas, I think I owe to explain the Euler expansion. So I will be just putting the reference here. Okay. Yeah. So, no. Just, yeah, this one. So, this is the series of function of the exponential x. So this expansion is derived from the Taylor series, if you know about Taylor series. If not, I think you should also look back to its uh look back to the Taylor series, no. So the value of the Euler or the exponential x, no, the expansion of the exponential x is being derived to 1 plus x all over 1 factorial plus x squared all over 2 factorial, so on and so forth. And yeah, it matters to how much the significant figures that you want for the value of the exponential functions. Let's say that you just want for 3 decimal values. It's up to you, or it's up to the situation, case to case basis, that you need a very accurate data for the Euler function, or you just need a very good amount of estimate, no, or dili kaayo accurate ang value niya. So it's just up to what type of situation or experimentation, or yeah, what type of mathematical use that you want to do with this expansion. Okay, and yeah, we have different kind of expansion with different kind of exponential series, exponential functions, no. So basically this one, so on and so forth. Especially for the trigonometric functions. So these are just being derived from the Taylor series. No? Uh, let's just no that the Euler expansion is just the Taylor series expansion. Okay. Okay, and finally, yeah, that's pretty much of it, no? And finally, we need to apply the differentiation formulas of exponential and logarithmic functions. So we have four useful differentiation formulas. First one would be the differentiation or the differential of the exponential x would be just equivalent to ex. And yeah, since we already know about chain rule, if we are about to differentiate the the exponential function with not just x, no, but a function of x, or just u is u is a function of x here. This is equivalent to eu times the du, no, such a way that you need to multiply a chain multiple, no, by chain rule. Number 10 would be the differential of b raised to the power of x would be equivalent to b raised to the power of x times the ln b. And same goes to chain rule. If the x is if the x would be replaced to a function of x, let's say x, a quadratic equation, so you just multiply it with du, no, if u is a function of x, or the differential to whatever is the equation of the exponent. Okay, for 11, that is the differential of the natural logarithmic of the absolute value of x. That would be equivalent to 1 of x. Same rule. So if we are to differentiate ln u, then it will be equivalent to 1 u times the du by chain rule. And last one would be the differential of the logarithmic x with base b, it's just equivalent to 1 or all over x natural logarithmic of b. So notice, you need to familiarize this formula. So these are very important formulas, no? Uh, the trick part, I think the easiest to differentiate are the 9 and 11. The trick part would be the 10 and 12, because this would be, uh, usually it's not very a mind friendly, no? You usually not, you usually forget about these formulas. But anyway, let's just have an example. Let me look for example. Let's start with, yeah, for a while. Yeah, I don't have examples here. Let's look at the book. Okay, ito sa libro for a while. So, yeah. Mhm. Oh, how about this one? So, let's differentiate f of x is equals to x raised to the power, no, x times the exponential of the negative x. Okay, so yeah, this are product of the x and the exponential x, so you need to apply, of course, the product rule first, and all throughout, you will need to apply the differentiation formula of the exponential function. So what we know is that, yeah, yeah, d of ex, um is just equivalent to, I don't know, differential of eu is equivalent to eu du, right? So by product rule, so the f prime of x would be equivalent to x times the differential of e raised to the power of x, that is e raised to the power of x, times the differential of the negative x, which is -1, plus e raised to the power of x times what? Differential of x, which is 1. So f prime of x would be equivalent to e raised to the power of -x times, yeah, 1 minus x. Ako lang kidit so og simplify. Okay. Yeah, how about this? Differentiate, let's differentiate y is equals to 8 raised to the power of -x. Okay, from the formula, which is equivalent to, yeah, this one, bx ln b, or let's say derivative of b raised to the power of u is just equivalent to, yeah, first copy du, then ln of the base times the du, no? So y prime would be equivalent to an 8 to the power of negative x times the ln of 8 times negative 1. So this would be equivalent to y prime to negative ln 8 times 8 raised to the power of negative x. Diba? That would be the answer. So let's go to logarithmic functions. So yeah, how about this one? Um, let's differentiate or derive y is equals to ln of x cubed plus 1. Okay, so yeah, we will apply chain rule for this one. So let's just say that the differential of ln absolute of u is just equivalent to 1 over x times the du, diba? So y prime is just equivalent to 1 all over x cubed times the chain multiple, which is 3x squared, no, plus 1, which is 0. So y is equivalent to 3x squared all over x cubed plus 1. Okay? Ano lang siya. So, yun na siya, no? Okay. Let's have another example. How about deriving ln of sine x? So that would be just equivalent to 1 over sine x times cosine x. Diba? So ln of ln of u is just 1 over u times the du, no? Then this would be equivalent to cosine all over sine x. In trigonometric function, this is equivalent to cotangent of x. Right? So, ano siya? It will be much more simpler. Okay. Last example for natural logarithm. So, let's derive um, f of x is equals to x squared ln x. So let's apply product rule. So the f prime of x would be equivalent to x squared times 1 over x plus ln x times the 2x. So this is equivalent to x plus 2x ln x. Okay. Or equivalent to x times 2 ln x plus 1. Just the same. Okay. Let's have a logarithmic functions. Uh, yeah, example. we have here to differentiate y is equals to x raised to exponents of x. So this is a good example. You cannot exactly differentiate directly this one because uh yeah, it's a variable to a variable, so it's neither an exponential, it's either exponential or yeah, uh it's a root function also, so it's a combination. However, one way to find the y prime here first is we need to take the ln of both sides. So ln both sides. So ln x to the power of x. So by exponential natural logarithmic law, so this ln y is equals to the square root of x ln x, right? Then we could start differentiating. So we know that y is a function of x. Differentiating the y would be y prime, right? So ln y would be 1 over y times the yeah times the chain multiple, which is the y prime. Then apply product rule here. So 1 all over 1 square root of x times 1 over x plus ln x times square root of x, which is 1 half uh x to the negative of 1 half, or just 1 all over 2 the square root of x. Ba? So yeah, um what is y? We know that y is just the square root of x, so you just have to multiply the right hand side to the x to the raise of the square root of x. So y prime is just x to the power of x times, what is this one? So square root of x all over x is just x 1 half minus 1. So that is 1 all over the square root of x. So 1 all over the square root of x plus the ln x all over 2 the square root of x. Yeah. You could combine the fraction here, so that is x to the power of x, which is 2 the square root of x all over 2 plus ln x. And you can have it as your final answer. Yeah. So if you have questions, you could chat. So that's it for the uh exponential and logarithmic functions. So next video expected would be the inverse trigonometric functions, and let's talk about the hyperbolic functions, no? So yeah, see you in the next video.